Am I audible, class? Let me know.
Sir,
Okay, and the screen is visible.
yes, sir.
Okay. So yesterday we have started the design of hopper bottom. Design of hopper bottom is nothing but the sloping slab that is provided at the bottom of the bunker. So in case of rectangular, in case of square bunkers, you have four sloping slab, and we have found out the distance, the dimensions, of the hopper bottom. And first, we need to find the self weight of the hopper bottom. Self weight equal to mean length into 4 because we have 4 sloping slab into length of the sloping slab into thickness. Here we have assumed thickness as 180 mm and into density of the concrete. Mean length, you see mean length 3 meter is at the top and 0.5 meter is at the bottom. So mean length is 3 plus zero point 0.5 divided by 2, which is equal to 1.75. 1.75 into 4 into length, the sloping length of the slab, that is 1.77 into thickness into 25. So self weight you're getting it as 55.76. And the weight of the coal is also acting on the hopper bottom. So the total weight of the coal is 352.40 kilonewton, and total load, we need to add the self weight of the hopper bottom. So after that, the total weight that you're getting is 408.16. Okay, so there are four plates, and this total load is divided into four plates. Okay, so we have this total load. Total load is 408.16 divided by 4 equal to, so the load on each hopper bottom is coming as, there are four hopper bottoms or four sloping slab if you want to consider. Okay, so the load on each slab is 102.04 kilometer. Okay, so this is the load that you're getting. So after getting the load, we can find the direct tension in the sloping slab. See, this is your sloping slab. This is your sloping slab, and we have direct tension in the sloping slab, and the weight is acting, not perpendicular to the, vertically downward. Weight is acting vertically downward. So whatever weight you have calculated, this is that weight, and tension is, it is parallel to the member. Okay, so I will write here direct tension on sloping slab, sloping wall per meter length. So whatever tension we shall be calculating, it will be per meter length. So that is equal to WT divided by sine 45 into L. Okay. WT, you have, just calculated weight on each sloping slab, that is 102.04. 45 degree is the angle, angle of the sloping slab, sine 45 into L. L is 3 meter. This length. You're talking about this length. The length of the hopper bottom at the top, 3 meter. Okay. So the direct tension that you are getting it as 48.1 kilonewton per meter. because we are finding direct tension per meter length of the hopper bottom. Okay. So we got direct tension. This is the direct tension, but it need to be factored because we are designing the bunker by limit state method. In the limit state method, everything is factored. The load is factored. Okay. So design direct tension is a factored load. Design direct tension equal to 48.1 into 1.5. That is equal to 72.16 kilonewton per meter. And this is the factored direct tension that is acting on the sloping slab. And we need to provide the reinforcement for the direct tension. And we know the formula. In the design of sidewall, we have seen the formula for direct tension, that is AST equal to TU divided by 0.87 into Fy. Okay, so we have the formula. We need to find the reinforcement for the direct tension, and this is that formula: TU, design direct tension, divided by divided by 0.87 Fy. Okay, and design direct tension, that should be in Newton, 72.16 into 10 to the power 3 divided by 0.87, and the grade of steel that we are using is 415, Fe 415, and Fy will be equal to 415. Okay, so AST that you're getting is as 199.48 mm square. Okay, and it is less than AST minimum. Yesterday we have seen what is AST minimum. We have calculated the minimum reinforcement in the bunker. We have calculated that. And AST minimum is 216 mm square. So whatever AST you will be getting, it should not be less than 216 mm square. That is the minimum reinforcement that you're providing in the bunker. If it is less than the minimum reinforcement, then you need to provide the minimum reinforcement. Okay. So we cannot provide 199 because it is less than 216. We will provide 216. We will provide 216. So AST equal to 216 mm square. Okay, so you see this is your sloping slab, and you have two face. On each face, reinforcement has to be provided. So AST on each face, AST on each face, that is equal to 216 divided by 2, which is equal to 108 mm square. So this is what you are getting. And now we can assume the diameter of the bar, and we can find the spacing. You know the formula of the spacing, how to find the spacing. So I will assume diameter of the bar as 8 mm diameter, and the spacing that I am getting for this, if I am providing 8 mm diameter of the bar, the spacing that I am getting is 465.32 mm. But you cannot provide this spacing because the maximum spacing is equal to 3D or 300 mm, whichever is lesser. So the spacing that you're getting is 465.32, which is greater than 300 mm. It means that whatever spacing you have gotten, you cannot provide that spacing. So you need to stick to the maximum spacing that is given by IS 4256. Okay. So I will write here, provide 8 mm bar, 8 mm diameter bar at the rate 300 mm center to center on both face. On both face. Okay, like this. On both face. This is one face and this is another face. On both face, you need to provide this bar. Okay. You also have to provide the bar for the normal pressure. You also have to provide the horizontal bar. So the sloping bar is for the direct tension, but the horizontal reinforcement is for the normal pressure acting, on the sloping slab. So we'll do that. Whatever reinforcement we have calculated, it is for the direct tension and it is provided on the both face of the sloping slab. Okay, it is parallel to the sloping slab, not perpendicular to the sloping slab. So next we have reinforcement in the horizontal direction. C, reinforcement in the horizontal direction. Reinforcement in the horizontal direction. To find the reinforcement in the horizontal direction, first you need to find the normal pressure acting on the sloping slab, acting on the hopper bottom. And we have seen the formula during our discussion, during our derivation. We have seen what is the normal pressure acting on the hopper bottom. When we have discussed, the design of hopper bottom, the derivation of the hopper bottom, what formula we have to use when we have to discuss the hopper bottom. Okay, so already I have given you the formula. So that formula I'm directly writing here. Pn equal to gamma h. H is different here. I will tell you what is H here. Bracket cos square theta plus sine square theta into cos square phi. Okay, so what is theta? Theta is the angle of the hopper bottom, that is 45 degree. Okay, and what is phi? Phi is the angle of repose. Angle of repose will be given in the problem. So I think here angle of repose in this problem, the angle of repose is given as 30 degree. Okay, it is something related to the angle of friction between the material and the concrete. Okay, so what is H? I will tell you what is H. So this is your bunker. Plus any question you have? Any question
No,
you
sir.
have? Somebody has written in the chat box. What happened, Shari? You have any question? Sharik, do you have any question? Okay. So this is your hopper bottom. So and above the bunker you have the surcharge like this. Okay. So what is this distance? This distance is this H is this. Half of the depth of the surcharge. And this is your H1. H1. This is H2. And this is H3. Okay. So why we have to take half? Because the material is not constant. It is a triangular shape. That is why we need to take half. H1 divided by 2 plus H2. We need to take the entire H2 because H2 is just like a rectangular portion plus H3 by 2. So that is your H. This is your H. This H you need to take. H1 by 2. Why H1 by 2? Because it's a triangular shape. We need to take the average depth, and below also, below the bunker also, it is a triangular shape. We need to take the average depth. So what is H? H equal to H1 by 2. What is H1? H1 is 0.87 by 2 plus H2 is 4.2 and H3 is 1.25 divided by 2. Okay. So this H we are getting it as 5.26. 5.26. Okay. So Pn equal to normal pressure acting on the sloping slab. Pn equal to gamma is given to you in the problem. They have given in Newton. You can convert that into kilonewton. In kilonewton, it is 7.85 into H, that is 5.26. Cos theta, theta is 45 degree. Cos square theta plus plus sin square theta, sin square 45 degree into cos square 5, cos square 30. So Pn equal to 36.13 kilonewton per meter square. Kilonewton per meter square. So, this is the normal pressure acting on the sloping slab. Normal pressure acting on the sloping slab. This is Pn, okay? And you also have to consider the, weight of the sloping slab, and the weight you need to consider perpendicular to the sloping slab. You need to resolve the weight, okay? So I will also consider the weight of the slab. How you are deciding, how you are considering the weight of the slab in the normal design of building? In the same way, you need to consider the weight of the slab. Normal component, see, weight is acting vertically downward. So that weight need to be resolved in the perpendicular direction, in the Pn direction. Okay, and that is Wt or Wd into sine theta, because this is theta, and the resolution of W in this direction will be Wd or Wt. I will take it as Wd. Wd into cos theta. Okay, normal component of self weight, normal component of self weight of sloping slab equal to Wd into cos theta. Wd into cos theta. So you know how we are finding the weight of the slab, self weight of the slab, thickness, depth of the slab into density of the concrete. So the depth of the slab that we have considered is 180 mm. Even in case of design of copper bottom, the depth is same, that is 180 mm. The depth of the sidewall is also 180 mm, and the depth of the hopper bottom is also 180 mm. Okay, so 0.18 into 25, depth of the slab into density of the concrete. This will give you the self weight of the slab. Okay, into cos 45, cos theta. So this is coming as 3.18 kilonewton per meter square. Okay. So total normal pressure. Total normal pressure is given as total normal pressure equal to 36.13, that is Pn, and this is also resolved in this direction. It is WD cos theta plus 3.18 equal to 39.31 kilonewton per meter square. So this is the total normal pressure, and again it has to be factored. Whatever load you have gotten, that needs to be factored. Okay, so PU, that is factored load, total normal pressure into 1.5. Total normal pressure is 39.31 into 1.5. Okay, so total normal pressure that you're getting it as total normal pressure, that is factored load, you're getting it as 58.97 kilonewton per meter square. Kilonewton per meter square. Okay. And you see, you need to take the mean length. This is your hopper bottom, like this. And already have taken the mean length. Here you have mean length, but we need effective length of the hopper bottom. So you need to, add the thickness of the sloping slab. Already have calculated the mean length, but you need effective length in order to find the bending moment. Okay. So with respect to the total normal pressure, we will be getting bending moment. To get the bending moment, you need effective span. So how to find effective span? Mean length has to be, mean length plus the thickness of the sloping slab, T by 2 plus T by 2, which is equal to T. Okay. So effective length equal to mean length, mean length plus T, thickness of the sloping slab, thickness of the hopper bottom. So mean length is 1.75. Already we have calculated 1.75, and the thickness of the sloping slab is 0.18 in meter. So this is equal to 1.93 meter. 1.93. Okay, now we can find the bending moment. Maximum negative bending moment in the sloping slab in the hopper bottom is maximum negative bending moment equal to PU into L effective square divided by 12. Okay, this is equal to PU, effective span also, divided by 12. This is, you are getting it as 18.30 kilonewton meter. Kilonewton meter. In the same way, you can find the maximum positive bending moment. Maximum positive bending moment is in the sloping slab in the hopper bottom is PU L effective square divided by 24. Okay. So this is equal to 9.15 kilonewton meter. Okay. So the reinforcement that we need to provide for negative bending moment, reinforcement has to be provided at the corners, and for the positive bending moment, reinforcement has to be provided at the midspan. We will see how to provide the reinforcement. when we see the detailing, RCC detailing of the bunker. Okay. So for whatever bending moment we have calculated, we need to find the reinforcement for this bending moment. Okay. So AST for negative bending moment. You can use the same formula. Yesterday we have discussed the formula, or if you have missed those class, you can see the recording. In the recording, you will get those formula. So I'm writing that I'm directly writing the values here. AST for this bending moment, negative bending moment, is 355.50 mm square. Okay, which is greater than AST minimum. What is the value of AST minimum? The value of AST minimum is 216 mm square. So your AST should be greater than 216. If it is not greater than 216, you need to provide 216. If it is not greater than. So here it is greater than 216. So AST is 355.50 is greater than AST minimum. Okay. You can take 10 mm bar, and the spacing that you will be getting as 220.89 mm, which is less than maximum spacing. Maximum spacing is equal to 3D or 300 mm. So we can provide this spacing. Okay. So provide 10 bar 10 mm bar at the rate 220 mm center to center at corners as horizontal reinforcement. At corners as horizontal reinforcement. Okay. Similarly, you can find AST for the positive bending moment. You can find AST for the positive bending moment. This is the AST for the negative bending moment. And similarly, you can find AST for the positive bending moment. AST for positive bending moment. Positive bending moment. You can use the same formula. And AST for the positive bending moment that you're getting it as 173.18, which is less than AST minimum. Which is less than AST minimum. Why you are getting lesser value? Because bending moment is less. The positive bending moment is lesser. That is why the AST value you are getting less. But it should not be less than AST minimum. If it is less than AST minimum, then you need to provide AST minimum. What is the minimum value? Minimum value is 216 mm square. So provide AST equal to 216 mm square. Okay, 216 mm square. So now what I will do, I will assume 8 mm bar. The spacing I am getting it as 230 mm, center to center. Okay, so it has to be provided at the midspan. At the midspan. Okay, now we will see the detailing. We have completed the design of the bunker. We have completed the design of the square bunker. In that, we have done the design of side wall. Yesterday, we have seen the design of side wall. And today, we have seen the design of the hopper bottom. So, which bunker we are designing? We are designing square bunker. The square bunker is little bit complicated. And the next topic is the design of circular bunker, which is bit easy as compared to rectangular or square bunker. Okay. So in the square bunker, you have to do lots of design. Okay, so I will show you the detailing. One second, not working. Okay. So here you have the side wall. Here you have the side wall like this. In the side wall, the vertical reinforcement are the distribution bar. I told you. The vertical reinforcements are the distribution bars. Okay. And the negative reinforcement has to be provided here. The negative reinforcement has to be provided here because in this line you will have the hogging behavior. Okay. This is the negative reinforcement. And the reinforcement for the positive bending moment has to be provided here. So this is the side wall I'm drawing. Okay, it's not hopper bottom. So in the side wall, you have seen the distribution bars are 8 bar at the rate 230 center to center. Not working. So this is your distribution bar, distribution speed. Okay. What is this? This is the reinforcement for the negative bending moment in the side wall. And that reinforcement you have gotten as 12 bar at the rate 150 center to center. You have written as corner reinforcement. Okay. You can write at the bracket corner or for the negative bending moment, whatever. For the negative bending moment, this is the reinforcement that you're getting. Okay. And this reinforcement the is the reinforcement for the positive bending moment in the side wall. And this is you're getting it as 10 bar at the rate 260 center to center. You can check the design. You can check the design. Okay. So this is the side wall that you have. Now we will see the hopper bottom. Just now we have designed the hopper bottom. Hopper bottom is like this. It is like this. Here you have the beam. We will not discuss about the beam. The design of beam is different, altogether different in case of bunker. Okay. So this part will continue like this, and this part will come at the bottom, and it will go like this. Okay. Here also the reinforcement in this direction, the horizontal reinforcement here is for the negative bending moment. And the reinforcement here at this phase, the horizontal reinforcement at this phase is for the positive bending moment. So just now we have seen we have calculated the reinforcement for the negative bending moment. So this reinforcement is for the negative bending moment, and we have gotten it as 10 pi at the rate 220 center to center. Okay. And this reinforcement is the reinforcement for the positive bending moment. And we have gotten it as 8 phi at the rate 230 center to center. And the reinforcement in the sloping slab is for the direct tension. Just when we have started the design of hopper bottom, after that we have calculated the direct tension. And because of the direct tension, you have calculated the reinforcement. And that reinforcement is provided parallel to the sloping slab. So this reinforcement is parallel to the sloping slab. Okay. And the value of that is both you have provided reinforcement at both the face of the sloping slab. So at both the face of the sloping slab, the reinforcement is for the direct tension, and that reinforcement is 8 phi at the rate 300 mm center to center. This is what you got. Okay, so we have completed the design of square bunker. You have any
हेलो सर।
question you can ask. Yes, yes, please.
सर वो 8 और 300 mm सेंटर टू सेंटर वाला जो आपने बताया है सर, वो ऊपर से कंटिन्यू में आएगा ना, बाहर नीचे?
नहीं, वो कंटिन्यू में आएगा, पर यहाँ पे आप ये अलग रहेगा, डिटेलिंग अलग रहेगा।
क्योंकि सर वो ऊपर वाला 230 सेंटर पे है और नीचे वाला 300 पे है, तो वो कंटिन्यू में तो सर स्पेसिंग दोनों का मैच नहीं कर रहा ना।
हाँ, चलेगा ना, तो आप वैसे नहीं प्रोवाइड करोगे। डिटेलिंग का मतलब इसको अलग देखो, आप साइड वॉल को अलग देखो। देखो, इसको अलग देखो आप। जरूरी नहीं इसका स्पेसिंग एक ही हो, अलग भी हो सकता है। आप यहाँ पे रोक देना। आई बात समझ में? यहाँ यहाँ पे रोक देना। जरूरी नहीं कंटिन्यू हो रहा है वो, बोल रहा हूँ। इसका जो रेनफोर्समेंट है यहाँ से शुरू होता है, जरूरी नहीं वो दोनों अटैच हो। अगर दोनों का स्पेसिंग सेम है तो वी कैन अटैच इट, बट दोनों का रेनफोर्समेंट अलग है तो नेचुरली वो पॉसिबल नहीं रहेगा ना। यहाँ पे 300 mm है, और यहाँ पे कितना है, इसका कितना है, इसका 230 है, तो पॉसिबल है ही नहीं वो। तो यहाँ तक कि आपको रेनफोर्समेंट प्रोवाइड करना है। ठीक है, समझ में आ गया मैं क्या बोल रहा हूँ?
यस सर।
हेलो। हाँ, अगर दोनों का स्पेसिंग बराबर है तो यू कैन प्रोवाइड लाइक दिस। अगर स्पेसिंग बराबर नहीं है तो आपको यहाँ से शुरू करना है। यहाँ से आपको शुरू करना है, ऊपर बॉटम का यहाँ से शुरू होगा। ठीक है। ओके।
यस सर।
एनी क्वेश्चन, एनी मोर क्वेश्चन? We have completed this topic, and in the next session we will take 10 minutes break, and we will start the next session. You have any question you can ask. In the next session we will start the design of circular bunker. Hello, anyone? You have any question?
No, sir.
Okay. So if you are confused, you see the recording, and still you are confused, you can ask the question to me. Okay. See the recording, learn the topic very well. After that also, if you have any doubt, you can ask me in the WhatsApp. I will reply in the WhatsApp. Okay. We will take 10 minutes break, and we will start the next session. I will take the attendance in the next session. Okay. Is it okay for you? We will
Okay,
take
sir.
10 minutes break.
Sir, can I leave?